In this video, I'm going to take a look at integrating with inverse trigonometric functions. Now, in the previous video, we had a look at differentiating inverse trig functions. And what we're going to do now is use the results from the previous video to integrate functions of the form. So the first form then is 1 over a squared plus x squared, and we also have 1 over the square root of a squared minus x squared. So the results that we need are given as follows. So we have the integral then of 1 over a squared plus x squared with respect to x. And as we can see, this is equal then to 1 over a arctan of x over a plus c, where the plus c here just represents our constant of integration. Okay. For the final result then, we have the integral of 1 over the square root of a squared minus x squared with respect to x. And as you can see here, this is equal then to arcsine of x over a plus c, where again, the plus c just represents the constant of integration. Okay. Now, these results are given in the form in the book, and you can use them when calculating other integrals without proof. However, you still need to be familiar with deriving these results. So on that note, let's take a look then at our first practice question. Starting off with question 1 then, which asks us to use the substitution x equals a tan theta to show that the integral of 1 over a squared plus x squared with respect to x is equal to 1 over a arctan of x over a plus c. So don't forget the plus c here just represents our constant of integration. So to begin with here, I'm going to start with the substitution then of x equals a tan theta. We have x equals a tan theta. Now, why do we start with this substitution here? Well, we know to transform this integral here, we need to replace dx. Okay. So if we start by finding dx by d theta, we can then rearrange and obtain dx. Okay. So dx by d theta should hopefully be nice and straightforward. In this case, we're going to get a sec squared theta. We get a sec squared theta here for dx by d theta. So in that case then, if we just want dx will simply be a sec squared theta d theta. Okay, so let's just write that down as well. We get a sec squared theta d theta. Okay. And now we have everything that we need here to transform this original integral. So we have the integral then of 1 over a squared plus x squared dx. Now, I can't do anything with the numerator as it is. We're going to leave that as it is. The a squared, I'm not going to do anything with that. However, what I am going to do is replace the x squared and the dx. And we know that x is equal to a tan theta, so we can rewrite the original integral here as 1 over. So we've got a squared here. We've got a squared there. We then have x squared. So if x is equal to a tan theta, we then have plus a tan theta all squared, like so. And then for dx here, well, dx is equal to a sec squared theta d theta. We have a sec squared theta d theta. Okay. Now, obviously, what I can do here then to begin with is take the 1 here, times it by a sec squared theta d theta. My numerator now is just going to simply be, let me just write down the integral sign. We're going to get a sec squared theta d theta. We get a sec squared theta d theta here. Okay, but I'll keep the d theta just outside as we would do for a standard integral. This is all over them. So I've got a squared plus a tan theta all squared. So clearly if I square this here, I'm going to get a squared tan squared theta. Okay, so we've got a squared plus a squared tan squared theta. Okay, so tan squared theta, what can we do with that? Well, we can use our trig identities here. Okay, now we know, let me just do it up here. So we know that tan squared theta is equal then to sec squared theta minus 1. sec squared theta minus 1 there. Okay. So I'm now going to replace the tan squared theta here with sec squared theta minus 1. So if I do this underneath then, we have the integral here of a sec squared theta. We've got a sec squared theta for the numerator. This is all over them. So like I said, we've got a squared here. Won't do anything with that just now. We've got a squared plus a squared times by sec squared theta minus 1. Like so. And this is with respect to theta. Okay, so d theta there. Now, clearly in that case then, if we expand this bracket out here, I'm going to get a squared sec squared theta. And then we also have a squared times minus 1, so that would be minus a squared. What's going to happen here is this a squared here will cancel with the minus a squared. Okay, so in that case, then this will cancel here with the a squared minus 1. Okay, so that will cancel there like so. What I get left with then is the integral of a sec squared theta on the numerator, or as my numerator I should say, so a sec squared theta all over. So we've now got a squared times sec squared theta here. So I've got a squared sec squared theta, and this is all with respect to theta. And from here we can cancel down. So clearly the sec squared theta and the sec squared theta here will cancel. So they cancel. I then got a over a squared. That will cancel, and I get left with 1 over a then. Okay. What I've got now is the integral of 1 over a with respect to theta. Okay. And given that a is just a constant here, we can now use linearity and take the 1 over a outside the integral here. Okay, so we can write this as 1 over a. We get 1 over a, and I have my integral here of 1 d theta. Or you could just write it as d theta, whichever you prefer. And clearly if I integrate 1 here with respect to theta, that would simply give me theta. So what I've got then is 1 over a times theta. So what we get then is 1 over a or theta over a, whichever you prefer. So 1 over a theta plus c. Okay, like so. Now clearly we're a little bit off what we actually want here because we want 1 over a arc tan of x over a plus c. We've got 1 over a times theta here plus c. So how do we get to the required form here? Well, we know that x is equal to a tan theta. So using x equals a tan theta, okay, I can rearrange here. So in that case, then tan theta is equal to x over a. So tan theta is equal to x over a. And therefore, if we just want theta here, I take the inverse tan of both sides then, or arc tan, whichever you prefer. And therefore, in that case, then theta is equal to arc tan of x over a. Okay, so arc tan of x over a, like so. And in that case then, what we've got here is 1 over a times theta, but theta is equal to arc tan of x over a. So therefore, what we've got here, 1 over a theta plus c is equal to 1 over a arc tan of x over a plus c as required. Okay, so what that gives me then is the original result that we need here. I'll write down the original result as well. So therefore the integral then of 1 over, we had a squared plus x squared with respect to x. That is equal then to 1 over a arc tan of x over a plus c. So 1 over a arc tan of x over a plus c as required. Okay, and there we have it. So like you can see there, that gives us the derivation of one of our standard results, and that also gives us the solution there to question 1. Moving on to question 2 then, which asks us to show that the integral of 1 over 4 plus 9x squared with respect to x is equal to a arctan of bx plus c, where c is an arbitrary constant and a and b are constants to be found. Now to answer question 2, I think it's about recognising what standard result we need to use. Now in this case, we're integrating 1 over 4 plus 9x squared with respect to x, so the result that we need to use here is given as follows. We have the integral then of 1 over, so we've got a squared plus x squared with respect to x. And this is equal then to 1 over a arctan of x over a plus c. Okay, where c is just an arbitrary constant as mentioned here. Okay. Now we do have a bit of a problem with the original integral. And hopefully you might notice this straight away. However, or what I should say is the problem here is the coefficient of x squared is not 1. Okay, so notice to use this result here, the coefficient of x squared will always be 1. In this case, given that the coefficient of x squared is 9, this does cause a bit of a problem. So how do we deal with this? Well, we just factor out whatever this coefficient is here. So in this case, given that this is 9, we're going to factor out a 9 here within the denominator. So let's just start by writing down the original integral here. So we have the integral then of 1 over, I've got 4 plus 9x squared with respect to x. So in this case then, factoring out the 9 within the denominator then, we get the integral of 1 over, so we get 9 lots here, and we get 4 over 9 plus x squared. Okay. And this is all with respect to x. Okay. What I can do now is take the 1 over 9 outside the integral using linearity. So we can write this as 1 over 9. And then we have the integral here of 1 over. And we've got 4 over 9 plus x squared here. So we get 4 over 9 plus x squared. And this is all with respect to x. And notice here then the integral that we have now is exactly what we want here to integrate. Okay. So in that case then, what I've got here is 1 over a squared plus x squared. So a squared equals 4 over 9. So a squared equals 4 over 9. So in that case then, a here is simply the square root of 4 over 9. So that would be 2 over 3. Okay. So in that case then, this integral here is just this standard result. We're going to get 1 over a arctan of x over a. So let's put all of this together. Now don't forget we do have the 1 over 9 here just on the outside. So I'll keep that on the outside for now. We'll deal with that later on. So we get 1 over 9 bracket. So I'm going to get another bracket here just to make sure that everything's clear. So I get 1 over a. So 1 over a where a is equal to 2 over 3. So 1 over 2 over 3. So 1 over 2 over 3. Close the bracket. We then get arctan. So we have arctan here of x over a. So I've got x over a, where a in this case then is 2 over 3. So we get x over 2 over 3, like so. Close the final bracket here, and then don't forget we're going to get the plus c. Okay. If we just simplify this as we go now, well, 1 over 2 over 3, that is the same as times in 1 by 3 over 2. So in that case, I'm going to get 3 over 2. I get 1 over 9, bracket, 3 over 2, arctan. Again, here we've got x, so I'm going to get x times 3 over 2. So I get 3x over 2. So I get arctan of 3x over 2. Like so. And then don't forget again the plus c here at the very end. And then finally, we just times through by the 1 over 9 here. What would we get? Well, I get 1 over 9 times 3 over 2. So 1 over 9 times 3 over 2, that would give me 1 over 6. So we get 1 over 6 arctan. Now I've got the 3x over 2 here. Obviously, we don't times that by 1 over 9. Let's just times it through by this coefficient here of the arctan. We get 1 over 6 arctan. of 3x over 2. And don't forget the plus c at the very end. Okay. And there we have it. So notice we've got everything that we need then. So in that case, we can see that a is equal to 1 over 6 and b is equal to 3 over 2. Okay, so we get 3 over 2x there, so b is equal to 3 over 2. Okay, and there we have it. So that gives us the solution there to question 2. Moving on to the very last question here then, question 3, which asks us to show that the integral of 1 over the square root of 4 minus 16x squared with respect to x is equal to a arcsine of bx plus c, where c is an arbitrary constant and a and b are constants to be found. So pretty similar to the previous question, I think the best place to start is by recognizing what standard result we need to use here. So in this case then, for an integral of this form, this would be an integral of 1 over square root of a squared minus x squared with respect to x, and this is equal then to arcsine. So we get arcsine of x over a, and again plus c, where as it mentions here, c is an arbitrary constant. Now again, we do have a bit of a problem with the original integral here. Again, notice use this result, the coefficient of my x squared here must simply be minus x squared, or we need minus x squared. What I have here is minus 16x squared. So again, we need to deal with this coefficient, and the way that we do that, just like we saw for the previous question, is by using factorization. Okay, let's just start by writing down the original integral here. So we're integrating them 1 over the square root of 4 minus 16x squared with respect to x. So now if we factor out the 16 here, that's causing us a bit of a problem. I get the integral of 1 over, so like we said, we've got the square root here of 16 times by 4 over 16, because we factored out the 16 here, so we get 4 over 16 minus x squared, like so. And this with respect to x. So we want to simplify this here. So if you think about the properties of surds, then I could write this as the square root of 16 times the square root of 4 over 16 minus x squared. And obviously the square root of 16 is 4. So what I actually get here then is 1 over 4 times the square root of 4 over 16 minus x squared. And the 1 over 4, just like we saw for the previous example, we can use linearity then and take that outside the integral. So what I get here then is 1 over 4. And then we have the integral here of 1 over. So you get 1 over here. Well, obviously 4 over 16 is the same as 1 over 4. So I've got 1 over 4 minus x squared. Okay, and this is with respect to x. So clearly in this case then, a squared is equal to 1 over 4. In that case then, a is equal to the square root of 1 over 4, which is 1 over 2. Okay, so what I've got here then is 1 over 4. I've got 1 over 4 arcsine of x over a, where a is equal to 1 over 2. So I get x over 1 over 2, like so. And don't forget our constant integration plus c. And then finally, we just simplified this bit here. What I get then is 1 over 4 arcsine. Don't forget that dividing by a half here is the same as timing through by 2. I get x, well, x divided by half, like I said, it's the same as timing through by 2. So x times by 2 would give us 2x there. So we get 1 over 4 arcsine of 2x plus c. Okay, and there we have it. So a in this case then, so a here is equal to 1 over 4, and b is equal to 2. Okay, And there we have it. So that gives the solution there to the very last question, question 3, and that actually brings us to the end of this video on integration with inverse trigonometric functions.